Welcome to Temple of Pone again. This week we're going to talk about SROP and then kind of talk about what it is and how to use it. So SROP, as in the title kind of suggests, it's like ROP, but it's called SROP for based on the SIG return syscall, and this is used mostly for context switching between threads or information that's running on the CPU and jumping between kernel activity, I'm pretty sure. Like, if you call a system call, usually you will call SROP at some point, or invoke SROP at a higher context. This is used mostly to keep track of user space information while the current thread or process is not being ran. So when it's not actually being used on the CPU, we need to be able to store the user space information somewhere, and this is usually stored on the stack. And what this does, it just retrieves all the values from the stack and will restore the current process. So this is kind of where the SROP uh, or vulnerability or technique kind of comes in, and it doesn't close your current process. So like even if you are just doing an SROP or the system call, it won't close your current process. You can just continue to keep doing it multiple times within the same activity. So from 0x41414141 CTF, they had a challenge called moving signals, where all it is this: move RDI 0, move RSI RSP, sub RSI 8, move RDX 1 F4 hex, and syscall, and then ret. So since RAX is never touched, RAX is going to be 0. So all this is doing is reading about 200 hex characters from the user onto the stack, and that's it. And then this kind of is a great position to do SROP on. So I'll go into exploit.py. Don't read that stuff. That's the finished version. Do that. P is equal to. Going to swap this up with GDB, and I'm not going to do it the normal GDB connect method because since the program is so small, GDB actually breaks the read and won't actually read incorrectly if you do gdb.attach. Pretty sure there's other ways to do it within Pwn tools, but that's just the way I'm going to do it. It's called moving signals p.interactive. Then we can just see what it looks like if I don't lose context. Exploit. Whoop. Gotta spell interactive correctly. So we start it. Get here, we can see that RX is 0, so this is going to be a read in a 64-bit. Just reads onto the stack. And then if we just put 2468, 2468, and we ret, we can see that we're going to go to our B's because it was -8. So the first 8 bytes are going to be eaten up by that subtraction, and then we get going. So it should be relatively simple for us to get something going with this. We're going to want a way to control RAX, and there's two kind of. The authors of the challenge were nice enough to us and gave us a gadget for it, but usually you won't have a pop RAX gadget. In that case, you'd have to use the read system. Ooh, actually you wouldn't be able to do that. Without the pop RAX, you might not be able to actually. I don't know, you could. So, without the pop RAX, you'd have to read in a number of characters to a system call you'd want to use to be able to get back. So the system call would fail or return 0 into RAX, so you can read again up to 15, because 15 characters alone won't be enough for SROP to work. In this case, you'd need to kind of do a backdoor method to get back to the 15 while having your values on the stack. I think that'd be the only way. Be really interesting, but we'll just use the pop RAX because I don't want to deal with that at the moment. So RX equals that. We can set up a quick chain. We have RX, want that to be 15 because that is the system call for SIG return. We can see that right here, 15. Doesn't take any other values or anything, just takes everything off the stack. So from there we can put whatever we want on the stack, but we pretty much just want the syscall, which if we look back at the IDA is at syscall is equal to 0x41015, and that should be it for the chain actually. Convert this back to text instead of a list. For chain, I think we should just be able to do p dot send line of chain. We should be able to see what it looks like. I'm gonna put in cyclic text right here. We'll do, I think 200 characters should be enough. Might not be. Let me check quick. Yeah, it should be enough. Let's go 300 just to be sure though. Okay, and then we're going to want to p.interactive because we're still running in the context of GDB first, so we want to get it started before we actually just send the data, otherwise GDB will intercept it instead of the program. So we can start, get to the syscall, send in our data. We can see on the stack all of our data is there. We read in 300 characters, and then, oh, I missed the off by 8. Forgot about that. So we'll have to do a times 8. And we should be able to get that. So pop rex, that goes 15, ret, and on this syscall we should crash. And we can see we have all these registers now filled out. So if we have another terminal open, we can figure out which ones we want. We want our DX, our SI, and our DI and RIP because we want to get an exec VE call. For some reason RX is showing 0 in these cases, but it definitely isn't, and I think it gets filled in right before our BX, but I can't be sure. We'll have to check that in a little bit. I think it might just be 0 because RIP gets put to a garbage value, so at that point it just crashes, but I don't think RIP is set before RAX. I have to check up on that, but it's just a weird circumstance. Could be just GDB intercepting it weird, but oh well. So our DX will go JAAB, that's at 136. Our SI was DAAB 112. Our IP is RAAB, that's 168. Our DIB AAB. And I'll just write those off to the side. 104, 168, 112, 136. Okay. Then, so we can go in here, just make up our, call this, we'll just call it the frame. And you'll see why in a little bit. Or in a little after this, I'll show you why I'm calling it frame. But for now, we'll just do P64 of 0 times. Let's see, we need to get to 104. 5 by 8 is 13. I'm pretty sure. P64. Then we set our DI, which we want to be bin sh, plus P64 of after our DI, our SI, that's 112. We want this to be 0. And we can just set that to, so 112 goes to 120, goes to 128, 136. Should be able to go 5, I think, so that should set our DX as well. Then we're going to do P64 of 0. Oh, we'll go 1, P64 of 2, plus P64 of 3, because I'm pretty sure RAX is somewhere in here after our DX actually. So I'm just going to set a bunch of these and see which one RAX is actually set to. So that should have brought us to 144, 152, 160. So do I need one more? I think I need one more before I need our IP. Then we'll just go back to syscall, because we should control all the registers at that point. So we can get rid of this guy and just put in frame right here. I think that should be good enough to look at the moment. Let me see if I missed anything. I don't think so. There's a good chance it won't be correct yet, though. Oh, Oh, bin sh isn't set. We'll set that to 0 for now. Start. And the reason we have that is because bin sh is actually in the... I'm pretty sure the challenge authors were also nice in this regard and just put it in here. So we just search for it, and bin sh is at 41250 because the / I didn't put it in there, but that's where it'd be at. Up Rx, rat syscall. Rx is 0, so maybe I overshot that. RCX, RSI, that's good. RDX, that's good. RDI is 0 because of that. RIP is 3, so I did overshoot it. RIP is 3. Ooh, I just overshot it by a bunch. Makes me think I overshot this one as well. So let's undo both of those and change this to a 3. Maybe I'm just off by a crazy amount. Set bin sh, make sure that one was right. So RDI, that's good. RX is 2 now. Our AX is 2, RDX is 1. So overshot it by 1, it looks like. No worries. So set this back to 4. Switch this to... we want this to be 59 for an exec VE. These don't matter anymore. We'll just set them to 0. Times 2, I think. Maybe it's... oh, I think I messed that one up too. Nope, it looks good. So we're at the syscall, we're at exec VE, we have bin bash. We should be good, except for we're going to seg fault if we do that. And the reason we're seg faulting is because of... ooh, I don't think it's because of these registers, but that might be because of the CS actually. I think it's because of the CS register. So right now the CS register is not in a great looking position. And the problem is that I think it's the CS register, but I'm not sure, but the CS register will control whether you're in 32-bit or 64-bit context. Yeah, that just doesn't sound right. A register controls whether you're in a 32-bit or 64-bit context, and at the moment we are putting 0 in that where it needs to be 0x33 or 0x23 to determine whether we're in 32-bit or 64-bit. And now we just need to put it in there. And at the moment, I actually forgot what the position was, but I think it's P64 0 plus P64 0x33. I think it's that. Oh, it was that. Awesome. And there, we got a shell. Now, it might be difficult or cumbersome to kind of work with this or create the chain every single time because you might not remember the offset that RDI is 104 characters in or 13 octets. So instead, Pwn Tools actually gives you a they have a class for it just called sigReturnFrame, where we can just set frame.rax equal to constants. We'll just call it 59 instead of doing the constants method. We do frame.rdi is equal to bin sh. I think it automatically sets everything to 0, but we'll just make sure that these two registers are 0. And frame.rap is equal to syscall. And then I think we should just be able to do that. So we'll comment this one out to make sure it's not messing anything up. And that should also set the 30... oh, that's not going to work actually. And I'll show you why. Because it needs the architecture to be specified so it can set the context and any other kind of return aspects it needs. Stat architecture is equal to AMD 64. Start. Can't concatenate. Oh, I need to convert it to a string. And there we go. same method, just a little bit easier to work with and kind of just looks nicer in the long run versus the really long chain of what are these two filling out right now, where it doesn't really matter, but these two do matter because they need to be 0 because that fills out RSI and RTX. That was kind of all I had. It was really quick, but SROP, as long as you understand basic ROP, getting SROP to work is kind of just the same, just you need to have stuff in the right position, and it can be really helpful if you have a system call and complete control of the stack to get what you need. Are there any questions?
I missed pretty much everything because I was at the gym, but I'll rewatch it.
Okay. I mean, you didn't really miss much. All I did was go over this one slide, which talked about what SROP is.
And that's a pretty good slide, though.
Okay, thank you.
Yeah.